Welcome to our discussion on basic trig equations. We're going to get into complicated ones in another video. So let's look at our objectives. Pretty simple. Just going to look at how we can solve basic trig equations and then how we can solve them by doing some factoring. So let's start with the most basic of trig equations, and that is where we have just a trig equation and a constant, right? So here are some examples of some basic ones. We've got the one that we're used to, sine squared plus cosine squared equals 1. And then we've got a couple other things that maybe you've seen, maybe you haven't seen, but they're all fairly simple in that they just have some trig stuff, and a constant. And that's about it. Now, of course, the identity is true for all values of theta, but the other two we would actually solve, and they're only true for specific values. And that's the whole idea, is to find those specific values. So whenever we have what we're going to call a basic trig equation, we have something where we just have one trig function and a constant. And then they can get a little bit more complicated where we maybe introduce a second trig function and things like that. But for now, this is all we're doing. Simple example. Sine theta equals a half. We've already dealt with things like this. We know where sine of theta equals a half. It's at pi over 6, or 30 degrees, right? Simple. But those aren't the only places where it equals a half. That's just for the reference angle. It also equals a half if we go over into quadrant 2, and we get 5 pi over 6. And then, of course, because we're now talking about a sine function that has a period of 2 pi, both of those things will repeat every 2 pi, right? So we can go from this pi over 6, we can go a distance of 2 pi will bring us back to here, right? Because 2 pi would bring us back to the origin, and then that pi over 6 would bring us up there. So we can go all the way around the circle from any point on the circle and get back to where we started if we just add 2 pi to it, or any multiple of 2 pi. So 2 pi times 3, i.e. 6 pi, you go around 3 times and you get back to where you started. And the same goes for 5 pi over 6, right? Go 2 pi, brings us all the way around, or 4 pi, we just go around twice. Okay? So that brings us to the idea that we have infinite number of solutions to these things. We know that the first solution is pi over 6, and that's the kind of the reference angle solution. And then the second solution within the period of the function, because the function goes from 0 to 2 pi, is 5 pi over 6. And those are the only places on one full revolution of the circle that equal a half for sine. And so then all we have to do is slap on any integer multiple of 2 pi, and that gives us the infinite number of solutions. And so to make an integer multiple of 2 pi, we're just going to take 2 pi and multiply it by k, where k is an integer, i.e. 1, 2, 3, 4, 5, 6, 7. And technically -1, -2, and -3, and so on and so forth. Okay, so you're going to be slapping 2k pi onto the end of any answer that goes with a trig function that has a period of 2 pi. And then what do you think you'll slap on the end of something for like tangent, where its period is pi? Hopefully you're thinking, well, wouldn't it just be k pi? Because it's an integer times pi instead of an integer times 2 pi. And if you were thinking that, you would be correct. Okay, here's a graphical representation of what it means to have all these infinite solutions. Because if you just have a horizontal line at a height of 1/2, right, that's what it means when you're looking for the output of a function to equal 1/2. You can see that it hits the sine function all over the place and in an infinite number of places. And here's the first two, right? And then in this little kind of like yellowy beige box is the full period of sine from 0 to 2 pi. And if we add 2 pi to each of these dots, we get the next two, and then the next two. And if we subtract 2 pi from it, we get that one and the one that's out there that you can't see. Okay? Let's look at a tangent example. Solve tangent of theta equals 2. Well, we can do that by taking the inverse tangent, because 2 isn't one of our standard regular pi over 6, pi over 3, pi over 4 angles. We don't get tangent equaling 2 in any of those spots, so we have to do it with a calculator. And if we round, we get 1.12 as an approximate answer. But as we just said, because tangent repeats every pi, then we have to add integer multiples of pi to it. But first we got to make sure that there isn't another angle within that 1 pi interval, right? Because that's the interval for tangent from 0 to pi. Is there another number that goes from 0 to basically 3.14, blah, 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 where tangent equals 2? And you should be thinking, no, there isn't, because if you remember what tangent looks like, it's kind of those lightning bolt shapes, and it's not going to cross a height twice, right? So instead, we're just going to add k pi to just 1.12. That's the only time that it works. And there's the graphical representation. So as I was saying, we can see that if we put a horizontal line at y equals 2, it only hits the curve once in each period, right? In each kind of set, in each instance of the function. So that's why we didn't find a second one within that 1 pi range, but it's going to happen at a distance of pi and multiples of pi in each direction. So that's why we have to add that k pi. All right, those are pretty basic. I mean, those are really basic. In the next example, we're actually going to have to do a little algebra. Okay, how about finding all the solutions to 2 sine theta minus 1? Well, when you do a little math, i.e. we're trying to solve for theta, right? So the rules still apply. You still do the same things you normally do, where you get rid of fractions, you get rid of decimals, you get rid of grouping objects, right? You combine like terms, then you isolate your variable, then you simplify, right? So we don't have any of those things to get rid of. So the first thing we want to do is isolate the term, which means add the 1 over, then divide by the 2. Now we've got sine all by itself. Once we have that, we could take the inverse sine of both sides if this was a number that we didn't know. But we know what sine of theta equals 1/2 is. We've already done that, in fact, in this video. But that's one of our special angles. So we know it happens at pi over 6 and 5 pi over 6. And then, of course, we also know because of the 2 pi period that we have to add 2k pi to each of those to get all possible solutions. Okay, what about the next one? Same rules apply, right? We get rid of fractions and decimals and grouping objects and blah, blah, blah. None of that to do in this one. So we isolate our variable, which means you move the 3 over. Now you've got tangent squared of theta. So again, we've got to simplify it a little bit further. So we have to take the square root of both sides. Remember, plus or minus, right? Because we're now solving for something. So plus or minus square root of 3 equals tangent of theta. And then to solve for theta, you've got to take the inverse tangent of that, or hopefully you remember that square root of 3 and negative square root of 3 are both 2 of our special angles. Okay, so those happen at pi over 3 and negative pi over 3, because you'll remember that inverse tangent is only defined in quadrant 1 and 4. So you go up to pi over 2 and down to negative pi over 2. So those are the 2 places where we get pi over 3 and negative pi over 3. And then, of course, just like all the others, you slap on the period multiples, right? So in this case, the period is pi, so it's k pi for both of them. Okay, how about if we have to do some factoring? We're going to make it a little bit tougher, but still pretty easy, right? Because the rules you use for factoring regular equations still apply to these. There's no difference between this and something with a bunch of x's. Instead of x's, you've got cosine theta or sine theta, but it's still the same idea. It's a variable, it's an unknown, so just think of it in your mind's eye as an x. So instead of 2 cosine theta minus 7 cosine theta plus 3 equals 0, hopefully you can look at that and recognize that that's a quadratic in disguise, because really all this is 2x squared minus 7x plus 3, right? Where x equals cosine theta. And so you could first think about how to solve this quadratic and set it up as, well, if I want to try and factor it, I know I have to do 2x and x, and then I have to have a 3 and a 1, and I have to, get 7 out of these things. So how about minus 3 and minus 1, because that gives me plus 3, but this gives me a minus 1 and a minus 6, and that works. Well, that's what's happening down here, right? See, here's my 2x minus 1. Here's my x minus 3. So you could always solve it as a quadratic with x, and then when you've got it, just substitute back in the cosine theta instead of the x. Or if this thing was in terms of tangents, put the tangent back in instead of the x, because cosine theta or tangent theta or secant theta or whichever trig function you've got is just x. It's just an unknown. Okay, well, if we were dealing with the normal quadratic, it'd be easy. We go, okay, either x equals 3 or x equals 1/2. So in this case, we get either cosine equals 3 or cosine equals 1/2. And hopefully you're already thinking, hey, wait a minute, cosine can't equal 3 because cosine has a minimum of -1 and a maximum of 1. So it's impossible for cosine to ever equal 3. And you go, that's right. That's an impossible answer. Remember, sometimes we get answers out of the algebra that don't actually work with the equation, and this is one of those examples. So cosine theta equals 1/2 is the only one of the two that works. So we go back to the circle and go, okay, when does cosine equal 1/2? Well, that's when we have a vertical line now instead of a horizontal line that hits at a distance of 1/2 from the origin, and we get two angles that do that, right? Either we go to pi over 3 or we go all the way around to 5 pi over 3, because remember now we're talking about cosine on a 2 pi interval, right? Because cosine again has a 2 pi period. So we've got pi over 3, 5 pi over 3, and then like always, we slap on those intervals, the 2k pi for cosines and sines and the k pi for tangent and cotangent. Okay, here's another example. And hopefully you're looking at that and going, isn't that kind of like 5xy plus 4y equals 0, right? We're just letting sine theta be x, cosine theta be y. And if I was going to try and solve for this, I think, well, I need a factor, right? Because the only way to solve something equal to 0 is to have factors. Because I know if I have something times something equals 0, each of the somethings has to equal 0. If I have something plus something equal to 0, I know nothing, right? That doesn't help me at all. So factor out that y, and you've got 5x plus 4. And now either y equals 0 or 5x plus 4 equals 0, which gives you 5x equals -4, which gives you x equals -4/5. Well, x, remember, was sine and y was cosine. So here is cosine and this is sine. And that's all we're doing down here is we're actually doing the same algebra, but we're leaving the cosines and sines in. So hopefully you'll get to a point where you can do the one on the bottom of the slide. It saves you a little bit of time. But if not, do the substitution, do the algebra that way, and then bring those trig functions back in at the end. Okay, so here's the same things we got, right? Cosine theta equals 0, or sine theta equals -4/5, which is -0.8. Now cosine theta equals 0, that's easy, right? When does cosine equal 0? Up at pi over 2, and then all the way around at 3 pi over 2, right? So 1/2 and 3/2. When does sine equal -1.8? Well, that's not one of our special things, so we would have to actually just take the inverse sine for that one. Okay, so to do the inverse sine, slap it in your calculator, figure out where it happens, and it happens at basically, right, all the way around at, well, it gives you -0.93 is what you get out of your calculator, but you have to remember that your calculator is giving you these two quadrants for sine, for the inverse sine, because remember we had to take the inverse sine to solve for theta, and the calculator only gives you answers in the two quadrants where the inverse sine is defined, and sine is defined in 1 and 4. So it's going to come back and give you an answer, obviously in radian mode, of -0.93. So you're down here at -0.93, almost -1 radian. And remember, 1 radian is not 1 pi, it's 1. Pi radians is 3.14, right? So this is about a third of a pi, right? So this is about negative pi over 3. It's pretty close to negative pi over 3, if you want to think of it that way. And then we can also get that height for sine, because we have to get that negative height. If we went around the circle the normal way, and since this has to be 0.93, in the negative, this distance over here has to be 0.93, and this is pi, so we get pi plus 0.93. Again, we need to figure out what that is as a decimal, so 3.14, blah, 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 add the 0.93, and we get about 407. So we go negative 0.93 or all the way around to 407. And those would be the two numbers that we could put in for theta, such that sine of it would give us roughly negative 0.8. But again, right, because sine has a period of 2 pi, we got to slap those 2k pi's on the end of all of our answers. And that's it, guys. Those are just some examples of basic trig equations.